Okay, well, let's go ahead and get started. So we're very happy to have Geoff Penington, who is going to tell us why life without pythons would be so simple.
Awesome. So yeah, thank you very much, Mark. So yeah, this is ongoing work with. Oh dear. I fear I have just lost connection to Zoom with my iPad. That is not good. Hang on.
Okay.
I think. Okay, now I'm joined, but now my old connection is still screen sharing, and I don't know how to stop it.
Are you host again?
I can't share
again?
screen because you cannot share screen while the other participant is sharing. Oh, here we go. This should work. Okay. Hopefully that's not going to keep happening. Okay. Okay, so yeah, this is ongoing work with Netu Narvin, and it's really follow up to a paper put out last December with Adam Brown, Grant Grobian, and Lenny Siskind. And of course, it is all fundamentally based on the seminal earlier work by de Saint-Exupéry. So one way to phrase this sort of paper last December is it's trying to answer the question of why is entanglement wedge reconstruction so hard to do? So let's sort of compare two different stories. One of them is sort of causal wedge reconstruction. So we have some operator here in the bulk, and you know we're trying to reconstruct it on the boundary. It's in the causal wedge, and roughly speaking, you can. Okay, so we have these two different setups. And one, it's in the causal wedge, and the reconstruction, the bulk operator, is basically just an integral over some simple boundary operators spread across the sort of causal diamond that we're reconstructing on. So to actually reconstruct this thing, say it's some like little unitary or something, basically all we have to do is some boundary time evolution and back and forth and turn on some little weak sources on the boundary, and we can implement our unitary acting locally in the bulk here. Okay. On the other hand, we can consider a setup with entanglement wedge reconstruction. So for example, we could have some bulk operator sitting in the middle, and we're trying to reconstruct it on two intervals on the boundary where it's within the entanglement wedge, but the causal wedge sort of stops outside it. And in that case, sort of the tricks we have for doing the reconstruction seem a lot harder, a lot less explicit. So you could use a PETS map, for example, look something like this. You could use modular flow to try and pull it out of boundary. We have various tricks, but all of them have a few features that generally they're sort of not very explicit. They rely on using sort of the modular Hamiltonian or the reduced density matrix of the state. So that's some very, very complicated operator in general. And they also don't have sort of a causal bulk interpretation, right? We can't think of this, that changing something here is just going forwards and backwards in time on the boundary and changing little things on the boundary. Instead, we're just fundamentally doing some non-local thing. Maybe they have some nice Euclidean interpretation, analytically continued Euclidean interpretation or something, but there's no causal Lorentzian bulk interpretation. So there's a particular important example of entanglement reconstruction, which was the main one we were thinking about in December, which is of course reconstructing the interior from Hawking radiation, right? Reconstructing stuff in the island. And so in that case, indeed, it's expected to be unavoidably really, really hard to reconstruct the radiation. That was a result of Harlow and Hayden a few years back. That yeah, even though the information is technically in the Hawking radiation, it's exponentially hard to pull it out. So we wanted to have some story about why that was true. And just to give you sort of a very heuristic explanation, our idea was the following. Let's say our bulk operator is sitting somewhere here. Okay, so this is our boundary we can reconstruct stuff from. And the minimal QES is somewhere behind the bulk operator. So if the bulk operator is in the entanglement wedge, we can reconstruct it. But in front of the bulk operator, we have some sort of non-minimal QES, but still, it's sort of a non-minimal constriction in some bulk Cauchy slice. Okay, so this is what you have, for example, for the interior black hole. It's what we have for the center of the bulk with the 2 interval case, lots of other situations. And our idea is that if you try to sort of map that across to an analogous tensor network, the tensor network might look something like this. So if you excuse my very bad drawing of a tensor network, what we have is we have one boundary out here to the left, and then it gets very small, has a sort of minimal cut in the tensor network, which I've drawn as just a single leg for simplicity. So that's like our minimal quantum extremal surface. Then we have this sort of bulging bit in the middle. Okay, that's the Python's lunch. It's like this bulging bit in gravity here. Okay, and that's where our bulk operator is sitting. It's in the lunch. And then it gets smaller again. Okay, and that's the sort of locally minimal cut is the equivalent of this non-minimal QES. It's like the second constriction. Netta sometimes calls it the appetizer of the lunch. It's like where the lunch starts. We're starting from the boundary at this end. And then it gets big again, and then we have this boundary. And we're wanting to reconstruct this bulk operator using boundary operators here. Okay. So how do we do that? Well, basically the only way to do that from a tensor network point of view is to use the fact that this whole sort of map from this minimal cut here out to the boundary is an isometry. Okay, if it's an isometry, we can sort of undo it, or we can undo it and leave some ancillas in the 0 state by doing some unitary at the boundary. So that brings us back to the state back here, and then we can remake it, but we can remake it with the bulk operator changed and played around with however we want. Okay, so that's what we're going to want to try and do. But to actually implement that isometry that maps here to here using simple unitary operators can be very, very, very hard. The reason it can be so hard is that even though this tensor network looks pretty simple, this tensor network has some non-unitary steps in it. There's some tensors in this map that going from left to right have more input legs than they have output legs. So as you try to sort of map step by step going from left to the right, the first few steps are isometries. They're easy to implement. But then to get from sort of the bulge to the locally minimal cut, we effectively have to do some sort of post-selection onto some particular outcomes. We have to do a linear map from a larger Hilbert space to a smaller Hilbert space. And that's a post-selection. So to sort of replace that post-selection by unitary state maps, first, initially you might think, oh, it's totally impossible to do. But we know it's possible because we know really we started with a particular state here, right? We only need our overall circuit to work for a starting state that's some state on this initial cut. And it turns out in that case, you can do this post-selection using unitary maps. You just have to use something called Grover search, which is just a quantum algorithm for sort of simulating the results of a measurement on a particular outcome that you want. And the trouble with Grover search is that the complexity required to do it is exponential in the number of qubits that you're post-selecting on. So what this does is it gives us a simple heuristic argument for why if we believe gravity is like a tensor network, then any bulk operator sitting here behind a non-minimal QES, we'd expect to have a complexity that's exponential in 1/q Newton, which is exactly what people have believed for a while, thanks to Harlow and Hayden, at least for the case of the interior of a black hole. However, there's an important point here, which is that this only explains why entanglement wedge reconstruction should be difficult if the operator we're trying to reconstruct is behind some other non-minimal quantum extremal surface. But it's easy to construct examples where something isn't behind a quantum extremal surface, even though it's not in a causal wedge. So here's a couple of examples here that are unfortunately chopped between pages a bit. But so one example would be we started with some thermofield double state. So the extremal surface is stating here. And then we like threw in some shocks from the boundary. We like did some time folds to make a long wormhole supported by shocks. And we're trying to reconstruct some operator in the middle of that wormhole from the right boundary. Okay, that's not behind any extremal surface. So we the Python's lunch doesn't provide an explanation for it being hard, but it's also not in the causal wedge. Here's another example, just an ADS Schwarzschild black hole, where a boundary region consists of like some relatively small region of the boundary. In this case, the causal surface looks something like this blue thing, but the extremal surface is the sort of nearest extremal surface is a bit further in. So there's a region that's behind the causal surface, but in front of the nearest extremal surface. So in this case, we have no explanation for it being hard, but the usual, the PETS map and stuff like that still seem like they could be doing some pretty complicated thing that would be very hard to implement. So that's really the question Nestor and I, and Arvin and I were trying to answer. One clue is given by this example over here. So if we have all these shocks, we made those shocks by hand by some unitary evolution with some time folds back and forth. If we made them by unitary evolution, we can also unmake them by unitary evolution. So we can just go backwards and forwards, removing shock, shock, shock. And then eventually we'll get back to the thermofield double state. And then this operator phi bulk suddenly will be in the causal wedge. Then we can reconstruct it, and we can go, we can just do causal wedge style reconstruction. It's all great.
Are these shocks classical or quantum? Is it like you send
these are, I'm thinking of these as pretty classical shocks. But we can maybe have them separated, but they can be separated by a large amount of time. This is just like the Schenker-Stanford style shocks.
Well, the reason is that Adam Boland gave this talk where he was saying that you couldn't remove the shocks.
Yeah, that's if you don't know where the shocks are. That's an interesting question, and I think would be answered by a story about finding pythons in unexpected places. But I'm not really going to have time to talk about in this talk. But the point is, in that case, he doesn't. The shocks were thrown in at an undetermined time. In this case, we're considering one particular state where the shocks was thrown in some particular places that we know. And in that case, we can just undo the shocks. Okay, my claim would be that in Adam Boland's case, then there's actually, if you consider the maximally mixed state in that code space, it actually secretly has a Python's lunch in it. That's a quick answer to why you can't decode it in that case. Okay. So our answer to this question is going to be that if the operator is not behind quantum extremal surface, then even if it's not in the causal surface, then we can still reconstruct it easily. And in fact, the way we can reconstruct it is to do exactly this process where we sort of change boundary conditions going forwards and backwards in time, gradually expanding the causal wedge each time until it gets very, very close to the outermost quantum extremal surface. Okay, so that's the vision. And of course, once we've done that, then it's inside the causal wedge and we can do whatever we want to it pretty easily, so we think. Okay, so let me first go through a sort of very simple example of how this can work. And that's just going to be sort of classical JT gravity, so 1 + 1 dimensional with some massless free fields in it. Okay, so we're going to imagine starting with a situation where we have some ADS2 here drawn very badly. We have some asymptotic boundary that's where the dilaton blows up that looks something like this. So we have a causal surface here, and somewhere behind that we have an extremal surface. Okay, so the causal surface has sort of positive expansion if you go this direction, sort of forwards and outwards. Also has positive expansion if you go backwards and outwards. And the reason that those are both positive is that presumably we have some sort of energy flux going across these surfaces that causes focusing and means that even though the dilaton starts expanding here, it doesn't blow up to infinity and it stays at some finite value. Okay, and so you have to be outside that in order to get to the asymptotic boundary where the dilaton blows up. Okay, is that clear? So then all we're going to do is we're going to use our freedom to choose the boundary conditions for this free scalar field to just cause these outright moving modes here to just get absorbed when they hit the boundary. We can always do that. We can just choose the boundary so that no left moving modes get created. And we're then going to get a space-time that looks something like this. So as we evolve forwards with those boundary conditions, these modes hit the boundary, but then just disappear. They never go back across here. We have no energy flux heading across this whole thing. And so what that ends up meaning is that there's no focusing happens in front of this past causal horizon. The boundary ends up coming further in, and the sort of new causal surface still lies on the same old past causal horizon, but now it has to have zero sort of future expansion. So it's actually the sort of outermost apparent horizon, future apparent horizon on that past causal horizon. So we sort of made the causal wedge a bit bigger by no longer having that energy fall in. Okay. Of course, it will still in general have positive expansion in the past outwards direction. So we're not at the extremal surface yet, but we made some progress on making our causal wedge bigger. Now, what do we do next? Well, now we just take the state up here, we evolve backwards in time, and we now use boundary conditions that kill off all these right moving modes that fell into the white hole. Okay, so we evolve backwards in time, and now there's no energy falls in. This asymptotic boundary ends up making it further backwards in the global ADS picture. Now there's no energy flowing across this past causal horizon. And so now this is the one that has to have past outwards expansion being zero. Okay, so you might think, oh, now great, we're done with this, both the expansion in this direction and the expansion in this direction, and now zero, and so we must have reached the extremal surface. But that's not quite right, because in general, there now may be some energy flux that have previously fallen in here, right? As a sort of left moving mode, but one that was previously behind the past causal horizon, and so we couldn't remove before. Okay, so now that can cause some focusing, and now our expansion in this direction at the new causal surface can be positive, even though later on it has to become zero. So we haven't quite reached the extremal surface yet, but we've certainly got closer. And now we can just start evolving forwards in time again, killing off this left moving mode that's falling in, right? So we evolve forwards in time, and that's going to push us out a bit this way, and then this way, and so on as we go forwards and backwards in time, lots and lots of steps. We call this the zigzag, as we gradually expand outwards and outwards and outwards, and eventually you can show that it's going to have to converge. The causal surface is going to converge on the extremal surface, or the extremal surfer, as apparently I wrote. So we can get all the way we want. At some point, the operator we want, if it's outside this extremal surface, it's going to become accessible, causally accessible, and then we can just fiddle about with it, make it do whatever we want, and then undo all our zigzagging and get back to the original state just with something changed deep in the bulk.
Quick question, Jeff?
Yep.
Regarding changing the boundary conditions, do you have a quick argument for why you can't do the same thing with the thermofield double, where you remove the Hawking quanta that reflect off the boundary?
I think because of your, I think you made that argument, Alvin, Ahmed.
No. The argument, so what we showed is that if you try to do it, you'll get a paradox, and simple ways of doing it end up inserting energy.
Exactly.
But in your discussion, it seems like you can just absorb.
That's because this is classical. That's because I'm focusing on the classical case here, and classically you can just remove all the energy, but classically there isn't any energy in the thermofield double state. So yeah, the quantum version of this you would have to think about harder. There's some paper I think it will still go through in the same way that you'll be able to get to the quantum extremal surface. You obviously can't get past it because of quantum focusing. And there's this paper by Arvin and Adam and Ronak that sort of showed in a simple case, then you can remove the amount of energy from here that or you can decrease the focusing here by an amount that's exactly how far it is outside the quantum extremal surface in a simple perturbative setting. So I expect the story goes through. I agree it is much more complicated. You have to worry a lot more about what energies are possible and what aren't. But yeah, for this whole talk, I'm just going to focus on the classical case.
Okay, thanks.
Okay.
Jeff, could I ask a related question?
Yep.
Even if you're free to do the coupling however you want and we don't worry about those subtleties, is there an easy way to see that you don't accumulate somewhere before the first extremal surface?
Yeah, you can, at least in this 2D case, you can bound the sort of amount that you're expanding it each time based on the expansions and the Laplacian of the dilaton, I think. And you can argue that you can only converge to a point that's extremal.
I see. Thanks.
You can any finite number of steps you can get past anything with positive expansion. Okay, but yeah, very good question. Okay, so that is obviously pretty simple, but that was just because it's 2D and 2D is very simple. What we'd really like is to have a story in higher dimensions. And honestly, we spent several months struggling with this thing. We now have it basically under control, but it's still pretty hard work. But we think we now have a story that works. So this is us being confused for several months. There's sort of various problems in higher dimensions. One is that you now have more sources of focusing than just sort of null energy. You have like shear and so on. Another is that the topology of the causal surface isn't even necessarily the same as the asymptotic boundary that you're interested in. So it's it doesn't make sense to just sort of like have no energy going in potentially, because then do you even end up with a asymptotic boundary with the same topology and so on. There's all sorts of different questions that we think we now have sort of answers to. But the real first one that you might have to worry about is, does an outermost extremal surface even exist at all? So you might worry, for example, that instead of a single outermost extremal surface existing, instead you have, say, a couple of extremal surfaces that maybe are time-like separated, or maybe they intersect, and sometimes one's outside the other, sometimes the second's outside the first, just sort of varies depending on position. And then there's not even a well-defined outermost extremal surface. Like the whole story would fall apart. So let me first give an argument that doesn't happen. And it's quite simple. We're just going to assume that it does. Assume we have these two time-like separated or intersecting surfaces. And then we're going to consider the respective sort of wedges, and we're just going to take the intersection of those two wedges. So this case, I've drawn them sort of time-like separated, the blue wedge and the black wedge, and their intersection is bounded by this red surface and is the red wedge. Okay, so there's a few different, potentially a few different parts of the boundary of this intersection. The first thing is it can contain part of the original extremal surface gamma 1. If at that point gamma 1 is just inside the wedge of gamma 2, then it will be part of the boundary of this intersection. Similarly, it can contain part of gamma 2. And then the other thing it can contain is something like this red surface here, where it's sort of past like separated from one of the surfaces and future like separated from the other surface. Okay. So then we have this new surface. In general, it will not be extremal. But what you can show is that each of these points will have either negative or zero expansion when you go sort of outwards to the future or outwards to the past. Okay, and the reason for that is pretty simple. So if it's part of gamma 1 or gamma 2, then it has zero classical expansion. And you can show that the quantum expansion would be non-positive by strong subadditivity. And if it's sort of future like separated from one of them, then the expansion in the future direction must be negative or 0 because of focusing. Similarly, going negative direction, it's like separated from this blue one. And so it must have negative or 0 expansion. And so everywhere on this new red surface has negative or 0 expansion. Then we use this trick called restricted maxi-min. We consider optimizing over all time slices that are anchored on our asymptotic boundary region plus this red surface. So all time slices going between the two. And then we maximize the minimal surface within that time slice by maximizing over time slices and minimizing within the time slice. You can show, because of these non-positive expansions, that the resulting surface can never end up hitting this boundary red surface, or if it does, it intersects an entire connected component. And that is enough to imply that the resulting restricted maxi-min surface is an extremal surface. But by construction, it is outside and space-like separated from both of our original surfaces. And so we've sort of resolved the problem. These two weren't really the outermost extremal surface. There was an outermost one that was outside both of them. Okay. Okay, so that's relatively easy. The hard part is going to be this step 2, which is going to be trying to show that if we have the causal wedge, some causal wedge that has positive expansion at the causal surface, then we can sort of fiddle around with our boundary conditions in order to make the causal wedge bigger. Okay, so basically our argument is going to be trying to show that we can always do that whenever it's positive expansion. And so the only thing that can stop us doing it is to have 0 expansion, and hence in both past and future outwards direction, and hence to have reached the outermost extremal surface. Okay, so this is the bit that just took a while to get right. And if you don't get it quite right, you end up just in a mess of GR calculations, and it all gets horrible. And even if you do get it right, it still gets a bit horrible. But yeah, basically it's going to be a matter of finding a completely general thing you can do that will expand the causal wedge just a little bit. Okay. And the way we eventually came up with to do this starts by doing the following thing. We consider a foliation of the space-time, and in particular the future causal horizon, by past horizons at different boundary times. Okay, so we anchor past causal horizon at some boundary time, shoot light rays in, they hit this future causal horizon, and we use that to sort of be a light coordinate on the future causal horizon. That's our coordinate V. We're also going to have a coordinate U, which has where the future causal horizon is at U equals 0. And we're going to have some transverse coordinates, which we're going to keep pretty covariant, which will be labeled by I and J. Okay, and we can always choose a coordinate system so that the following set of gauge conditions are true. We have that this future horizon is null, so we can make G UI be equal to 0. Sorry, yeah, the past horizons and the future horizon are both null, so we can make G UI be null everywhere, make GVI be null on the future horizon. We have GUU be 0 everywhere, GBV be 0 on the future horizon, and GUV be 1 everywhere. Okay, this is a set of gauge constraints we can do. And then we're just going to do the following trick, which is basically going to be the central trick, but it has to be done in the right way. Which is we're just going to take everything on the future causal horizon and we're going to stretch it out a little bit. How is this going to help? It's going to make all the energy fall in later and hence sort of have less focusing effect because it happens later. And that's eventually going to end up causing the causal wedge to get a bit bigger. So formally, we're going to say that our new sort of metric on the causal horizon is just going to be, on the future horizon is just going to be the old one stretched out by some factor of 1 minus epsilon. Okay, this also stretches out the null energy falling in by a smaller amount. Okay, so if this is all we did, then it would just locally be a diffeomorphism away from the causal surface. And it certainly hasn't changed the size of the causal wedge yet, because this future horizon is still light-like in exactly the same way as before. But because we've stretched out everything in front of the causal surface, but not stretched out stuff behind the causal surface, then what we've done is create a sort of discontinuous drop in theta in the future expansion at the causal surface. So sort of here, the expansion is as it was before, and it's positive, obviously, because it's a causal horizon. And then here it suddenly gets smaller because we stretch stuff out. Okay, so that means we're no longer satisfying Raychaud-Dorris equation at the causal surface, unless we say suddenly had some null energy sitting here, which we don't. Okay, so then step 3 is that we're going to perturb the metric in order to recover our constraint equations. In particular, we're going to perturb delta GVV. Okay, so GVV was previously equal to 0 or at u equals 0 on the future horizon. That's just saying that the future horizon was null. We're going to perturb it slightly. We're going to make the future horizon not quite null. So it's not going to be the future horizon anymore. And hopefully it's actually going to be outside the future horizon. Okay, so this is just showing the same thing I said before. So behind the causal surface, the expansion is unchanged. If we had no sort of delta GVV getting turned on at the causal surface, then there'd be a sudden drop in the expansion theta b. Okay, but if we do turn on a delta GVV, particularly if we turn on a slightly negative delta GVV, making the causal surface slightly time-like, then the new null surface now goes outwards, further outwards like this. Okay, so it gets a bit of extra expansion from the positive expansion going outwards towards the past. This makes it slightly bigger, and we can make it the same as the expansion was before. We can sort of locally satisfy the Raychaud-Dorris equation again by turning on some negative delta GVV, by making the old horizon slightly time-like near the causal surface. Okay, that's already well, but now you've started perturbing the space-time, and you have going to also have to perturb stuff further to the future, and you could worry that maybe it gets locally time-like, but then later it has to become space-like, and you haven't actually expanded the causal surface at all. Okay, so this is when you need to get a bit cleverer. What you do is you just look at the perturbative change to Raychaud-Dorris equation and get it to give you an equation basically it just gives you an equation for the delta GVV that you need as a function of v and the transverse coordinates in order to satisfy Raychaud-Dorris equation everywhere and not have any violation of the constraint equations. You might say, by the way, there's also other constraint equations, but they'll just give you equations that tell you how to perturb the u derivatives of the metric. So we're not going to worry about them. They're not going to be important. Important thing is going to be Raychaud-Dorris equation. There's a load of messy stuff in here. It's kind of complicated to work out. But the key thing is that we have this theta u here, which because we chose our v's very carefully to all be sort of past causal horizons, these are all going to be positive, or sorry, they'll be negative, I mean, because they're on past causal horizons. And we have this sort of Laplacian term, and that Laplacian term has a negative sign in front of it. And what that means is this whole equation is something called what Netter would call a parabolic PDE, parabolic partial disequation, what I would call basically a heat equation with some extra messy stuff added in. Okay, and then you can apply some very powerful result that Netter calls the maximum principle for parabolic PDEs, and I call a relatively intuitive fact about how PDEs that look like the heat equation work. So what is that? It's that if delta GVV was negative everywhere at v equals 0, i.e. at the causal surface, which it was because we had this discontinuous drop that we needed to correct with some delta GVV source, then actually delta GVV can never change sign. And so the old causal horizon ends up being time-like everywhere, not just at the causal surface. So why is that? Well, let's suppose that at some point the max value of delta GVV becomes 0. Like it's trying to go from being negative everywhere to being positive somewhere. So the max value has to increase through 0. Okay, let's look at what these terms would do. We have this Laplacian style term. Okay, because it's a maximum, that Laplacian term will want to decrease delta GVV, like the heat equation, right? It wants to smear it out. It's negative everywhere around it. It's 0 there. Wants to smear it out and flatten things so that it becomes a bit negative at that point as well. Then we have this term that's the twist times the gradient of delta GVV, but it's a maximum, so the gradient is 0, so that does nothing. And we have some complicated stuff times delta GVV, but delta GVV is 0, so that does nothing as well. So the only thing causing delta GVV to change with V at this point is this Laplacian term that wants to decrease it. So delta GVV can't increase, it has to decrease basically, and so it can't go through 0, it has to stay negative. Okay, you can prove that more rigorously, but that's the intuition. Okay, so what that shows is if delta GVV is negative everywhere, then by perturbing the solution in this way, we found a sort of new horizon that satisfies the constraint equations everywhere, and that has a bigger causal wedge because the old causal surface is everywhere time-like separated from the asymptotic boundary. Finally, we want to argue that we can actually do this perturbation of the future horizon without changing the past horizon, just by sort of evolving forwards on the boundary with appropriate asymptotic boundary conditions. So this is just a argument that you can sort of solve a non-standard Cauchy problem where you sort of start with a state on the two horizons and you evolve it radially outwards using Einstein's equations to get some state on the asymptotic boundary. That state on the asymptotic boundary, space-like state on the asymptotic boundary, would just be the asymptotic boundary conditions that you need to use. So with enough appeals to PDE theory and maybe some assumptions about things not going horribly wrong, you can argue that this is possible. And that we have found some boundary conditions on the asymptotic boundary that will increase the size of our causal wedge. If we can do all that, we can just sort of gradually go forwards in time, making the causal wedge a bit bigger, go backwards in time, making the sort of a bit bigger to the past, forwards, backwards, so on, zigzagging our way until eventually we'll be forced to conserve to the outermost, converge on the outermost extremal surface. Then we fiddle with the thing we want to fiddle with and undo it all. And we've successfully changed something sort of, anything that we want in the outermost, outside the outermost outermost extremal surface. And we've done so sort of only doing bulk evolution with some sources turned on at the boundary. So that's pretty simple. In particular, it's not exponentially hard with respect to 1 over G Newton. Okay, so that's basically all I'm going to say because I'm out of time. I did just want to tell this story of how it works in detail because it's took us a lot of work and we think we're now done with it. So I wanted to show it off. But let me just end with some basic comments. The first is getting back to Ahmed's question from a while ago, which is, of course, what we really care about is quantum fields, quantum extremal surfaces, and so on, not just the classical version of the problem. And yeah, we would love to do that in full generality. But honestly, even doing the classical one with full generality is hard enough. We're hopeful that the quantum story should be very similar. So there's this paper by Arvin, Adam, and Ronak that does it in the special case of sort of vacuum ADS, where you're just trying to pull you have a quantum extremal surface that's perturbatively outside the classical one, and you want to pull the causal surface out from the classical extremal surface to the quantum one. But just generalizing, and the trick that they use is sort of a very similar stretch of the things on the future causal horizon to the ones we're talking about. But like generalizing that quantum version of the stretch to arbitrary curved spacetimes and so on, showing that makes sense seems pretty hard. But yeah, you could eventually hope to have it happen. If you did, it certainly wouldn't expand anything for the thermal field double because of the quantum focusing. So let me also make two more comments. The eventual vision of all of this, I focused on the details of how we actually do an expansion for this talk. But the eventual vision is we want to argue that Python's lunches are the source of like all the very large, in particular, all the exponentially large complexity in the holographic dictionary. And we have arguments that I hadn't time to talk about that this is true, even for examples where there's sort of not obviously a Python's lunch. So one of them is just interior partners of Hawking pair in the interior of non-evaporating black holes. Another is the one mentioned of Adam Boulan's and co.'s construction, where you have shocks that fell in, but you don't know when those shocks were thrown in. There's various situations where you might think something's very complex, but there's no Python's lunch. But actually, if you look hard enough, then you'll find that there is one. And in fact, it gives the right answers for the complexity of those things, the Python's lunch. I also want to emphasize that even the story I told today, there's a lot of possible subtleties we're still trying to get control over. Things like non-compact causal surfaces and stuff like that seem significantly harder. You run into more PDE problems. There's all sorts of other like potential ways the whole thing could fall apart that we're still worrying about. But as of right now, we think it all works. So thanks for listening.
All right, thanks, Jeff. So we have time for questions. So let's start with Jonathan.
Hey, Jeff. Nice talk. Thank you. I was just wondering if you could comment on, well, I think you hinted at it here with these non-compact causal surfaces. Can you give an example of when the causal surface will have different topology than the surface on the, than the asymptotic region that you're considering?
A very simple example would be just take two black holes, like take a single copy of ADS with two black holes in it, right? And you make them two eternal black holes that maybe will merge together at some later time, but they're black holes that previously were white holes. Then the causal surface will be like two spheres, and the asymptotic boundary will be one sphere.
Oh, okay, sure.
Merge together. Yeah. My point was just, the most naive thing you might try to do is try to create a space-time where you just glue in like a fixed, like, there's various stupid things you might try to do of like just constructing by hand a sort of particularly simple geometry with no focusing starting from the causal surface. But if you do that, it's very hard to argue that you're actually going to end up with a sort of asymptotics that look similar to what you had before. So that's why we go with this approach of like slightly perturbing the solution you had before.
Right, that lets you have topology change, I guess, as you go along. Is there, and there's nothing in this construction that requires you to be working with the entire asymptotic boundary. This is fine for subregions, right?
I would certainly hope so eventually. There are potentially more issues with like if your causal surface is non-compact, then you have questions about like the maximum principles you need to apply. You need to be a bit more careful with.
Oh, I
see.
You
also might worry that like the perturbations out near the asymptotic boundary are somehow completely messing around with your asymptotic boundary conditions. Say your boundary region has shear, for example. Then you can worry that if you're like getting rid of focusing there, then you're like messing up with the shear of the asymptotic boundary region and stuff. So there's more things you need to worry about. My personal...
Yeah, I don't feel worried about that, but I appreciate your moderation.
I mainly think Nature is more worried about it than me, and so I'm trying to give the team feelings on it as accurately as I can. But I certainly think there are reasonable worries, and the compact case, like entire connected component of the boundary, feels safer.
So the next question is from Ying.
Jeff, can you comment on where's the Python's launching Adam Boland story?
Yeah, Yeah, this will then be really nice to have my iPad. Good. So the Python's lunch isn't there in the particular pure states he's considering. But the point is, if you want to do entanglement wedge reconstruction, as discussed by Chris and so on, and yeah, you need to have the thing be in the entanglement wedge, not just for one of the particular states, but for all the states in the code space, right? And in particular for the sort of maximally mixed state in the code space. And if you have a maximally mixed state in the code space, then okay, what happens is that you can now no longer just absorb the shocks necessarily as they come back and hit the boundary. And so those shocks will go out to the boundary, and then they'll fall back in, and they'll get very close to the horizon. And it's sort of a scrambling time in the past after the first one falls back in. Then you'll end up with a quantum extremal surface just slightly inside the horizon, just for the sort of usual reasons that they happen with evaporating black holes and so on. It's just a very general, basically, anytime you can't make anytime there's no way to get the vacuum state locally near the black hole horizon as you go into the past, then you're going to tend to end up with a quantum extremal surface just sitting there, and you can argue that happens in this case.
I thought their intuition behind this high complexity is that you don't know how you prepare the state, so you don't know.
Yeah, exactly. That's what I mean by you don't know which preparation was used. And so if you wanted to do some reconstruction of it, it would have to be a reconstruction that works for any state in that code subspace. Okay, and in particular for like a mixture of the different states, a mixture of a state of shock thrown in at time t1 and shock thrown in at time t2 and so on. So those have a mixture of shock thrown in at time t2 and no shock thrown in at time t2. That mixture, that gives like extra generalized entropy, basically. Gives extra bulk entropy from the super mixture of like having the shock there and not having the shock there. And that's what leads to the Python's lunch.
Okay, thank you.
So Daniel, next question.
Yeah, so I just wanted to understand a bit more the limits of this idea that Python's lunch are the source of all your problems. So certainly in complexity theory, post-selection is not the only source of difficulty in computation, right? So I
would argue that maybe in tensor networks it is.
Yeah. So I think right, because I could just have some horribly complicated state in the bulk, right? So
yeah.
So I think you're implicitly sort of talking about states that you prepared in, where if you knew everything that was going on, there would be some simple way of preparing them. I'm
talking about simple bulk states, I think. Though let's see. So yeah, I guess you could worry that if the bulk state itself was exponentially complicated, if I have some very, very complicated bulk state, then I could have a situation where even though I can like change things like causally from a bulk point of view, just doing so is exponentially hard. Like doing the changes to the bulk state, even if the individual operators I need to do are very simple, then it can be very high complexity.
Or it might just be that you don't even have a picture of the whole bulk. Like if you have like just a hard typical microstate of a black hole. Probably we think that the interior is exponentially, you need to do something exponential. And I guess currently I don't see why there should be a Python's lunch there.
Let me phrase my claim in the following way. The source of, I'm going to call the source of exponential complexity in the dictionary, where you can't see anything exponentially complex in the bulk. The bulk looks pretty simple, but suddenly on the boundary, it's exponentially complicated.
Yeah.
Yeah.
That sounds okay to me. Thanks.
Lenny, do you still have a question? You had your hand up before.
No, my question was answered. In fact, my question was Ying's question.
Okay.
Yeah. Good.
Okay. Any other questions or comments? Okay, well, if not, let's thank Jeff again.